project and you need to do a thermal analysis of something, it look pretty cool if you did this yourself. This is what we expect to see in service. Okay, so actually that ran pretty fast, so that's pretty cool. I don't think it's gonna run as well on this thing, but all right. Let's see, I think I made a different folder for y'all here. Anybody have any questions on that right there? Let's see the code or anything, or I like to say that it uses a subroutine, or a function called plot. I called it plot temp, and like I said, I'll send it to you, and you can try it out and see how it works. All right, so we were in the process, if you recall, that we had made a grid of points, and what we're trying to do is to get a connection, some way to tell the program which grid points are connected or which are in proximity to the current one. And if y'all recall, just to kind of check to see where we're at, since we're going to do this matrix free, what is the only way that we can solve our system that we know at this point? We talked about kind of solver. It's named after two guys. Yeah, we have to use that right there. So we're kind of married to this idea of using that iterative solver. Okay. All right. So keep that in the back of our minds that we're going to have to, once we get everything connected, we're going to be able to pass this to an iterative solver, and we will take a reasonable guess and then go off and see how that works. This is going to take us a little while to get this done. So it's going to be just a day or two, just kind of programming here. All right. All right, so I think what we were doing here is we were establishing neighbors, and I think we got the northern neighbor established. Okay. Let's kind of run that and sort of see if it makes a sanity check for us, how it does. That's the other class that likes the y'all care. I don't really remember octave function this slowly. Does it seem like everything is worse today? It's really slow.
Like all devices have been working bad for a week.
That's what Control Z is for. That doesn't work. Thermal pipe. And you want to check to see if first if this thing runs, and of course it doesn't, so we'll see what went wrong. It's line 59. So, kind of coaching you on some debugging tips. So nice thing about MATLAB or Octave, it'll tell you what's wrong with 59. So I can go through line 59. Type it. And it got 59, so I probably need to mic in. Let's see, this is the so I need probably a pair, I need two more end statements. Let's try that. check on what's going on with this. Good grief, that is slow. Well, while that's doing all that, put this over here. Let's see where we are. I don't know what that means right there. Hopefully that's not nothing. If y'all see anything that's coming, that's causing so much, trouble here? Tell you what, one of my tricks is when nothing's working right, or when you got problems, I'm gonna just comment out a bunch of code, at least see if I can isolate where it's coming from. Strong suspicion is this last part, so I'm just comment all these things out. Thinking, if you're using MATLAB, I think there's a, fast comment block that you can do to make everything clear real fast. And just go back here and do our plot again, and just take this out, make sure we're at least as good as where we were at one point on, and if you haven't figured out Control C, if you're using, will kill you, at least on those, will kill you. On Mac, I think will kill you. Alright, so let's try this here. Alright, so we're doing great, made our picture, so that's all good. So something, and y'all kind of help me out here, something down here is not happening with me.
Elton's on the fourth and fifth line, or third, fourth line, you just have that song.
Appreciate that. So cross our fingers, that's all it is. We can live with that. Alright, so let's see what's wrong with our deal. Alright, so let's see what we found here. We should have some neighbors, and we should be able to look at a few points and make sure that they make kind of sense here. So, let's look at our data structure so that we're kind of on board. And like I say, y'all are obviously free to use some other tracking method. But I'm gonna look at, just check out our neighbor right here. So this is all of our neighbors. So we got some good northern neighbors that we probably found. And let's look at, say, neighbor, let's just look at 200 if it's not zero. That's the neighbor 200. Nate's got two arguments, so x of 200, big X of 200. Y 200. Alright, so we got that right there. I wanna say, so that is 201. Let's do a different one. Let's do Nate. Let's do, let's just do 138. Not really liking that very well, so we'll do Y of 139. And Y 138. I think we got some logic problem right there. No, actually, the one is a little bit higher than the other one. And the X's should match, so say X 38. Okay. So actually, maybe it's working. I'm a little surprised that it's coming out to be quite that way, but it's kind of weird. So if I do this point right there and we do the X 139. Alright, so maybe that's working. I'm just kind of surprised that it happened to be one above it. I think we were numbering our rows going, like if we were plowing a field, we were going east and west and then turning and then going to the north. So I'm a little surprised that no matter what we seem to put in, it's coming. Anyway, I'm pretty sure we're going to have to go back and debug that, but it seems like it's working. Okay. Do I have an explanation for why no matter when I put in 200, it was the next one, and I put in 138? Maybe I was laying things out on a north-south basis in terms of numbering. Yeah, I guess we were actually, because it was a nested loop, so that's cool. All right, has anybody got any questions on that? All right, so we're going to do today, I'll be pretty happy if we get this whole process repeated, and we also find the ones that are on the boundary. So if their neighbor, if it doesn't find a coordinate, it's going to stay at what value, just for reference. If it doesn't find like a right neighbor or an east neighbor, what's it going to have?
Isn't it 777?
Yeah, or minus 777. So that's our kind of our flag for that. Now that I think about it, we probably need to kind of pad our region a little bit more than what we did. In other words, what I'd like to do is make my blanket set of grid points go a little bit further than the outside of the pipe. See how we defined our del. Let's see, put R, I guess that's okay. I could probably make that a little bit bigger. Go a little bit further outside of the pipe, so that should be okay. Some of these won't have coordinates in them. I'll make that right there, so that should be okay. Alright, so let's kind of continue with the logic then. It seemed like it worked. Let's see here, we got all these right here, so we just need to, we can recycle this dx and this dy, and we can kind of get east and west kind of put in here and south as well. So since we're on the same column, we should be able to get the south, this one up here was, one for the north. And we should be able to, get the southern neighbor as well there. So we said that DY was greater than that, and less than that, then we're northern. So we gotta do the opposite then, so, so let's try this and see if this makes sense. In this case, DY should be less than, so let me just think about this out loud. So here DY is gonna be a negative value, and del low is gonna be a negative value, and del high is gonna be a negative value, and del low is gonna be a lesser negative value than, actually it'd be a greater negative value than del high, so they're both times minus one. Alright, so I might have to put a comment in there to keep all that straight, so for the southern neighbor. Actually, how did I put that? How did it come up with the del high? Oh, well, actually, those are just values. Go to my definition. Okay, that ain't gonna work, I don't think. So we need a negative version of this too. Actually, that you can recycle that, we just have to multiply by minus one. This is pretty tedious. Alright, so that's basically saying that, DY should be. Actually, it should be less than that. Should be greater than less than that. Alright, so that's greater than minus 30. Plus 30. Alright, so I think that could do it. Take a look and see how that program's out. Did we get anything in our 3D column? didn't find anything, so something went wrong. Y'all help me find out what, is wrong with this logic here. So we got our DY, and it's, defined as the neighbor minus the home value, so when we get a southern neighbor, it should be a negative value. Negative value, but that's- I have so many things here, kind of keep these up, so we got, these are over L home and L neighbor. Let's see. That's what I can do that. It can drive here, that's what's wrong, so. We never found a southern neighbor for sure, so let's see what's going on there. Alright, so, we did find some northern neighbors, so that's cool. And let's just see what's going on here, so we got, why in the world are we not finding anything like that? Should have some small negative values here, so let me take this off and see if we're getting some. Gotta get some small negative values. Seeing some small negative values. So it's cool. All right, with y'all's eagle eyes, y'all see what's going on wrong with this here. I'm not trying to make a mistake on purpose, but. Do I need to subtract off a little bit here? Okay, that possibly is what's wrong, is that my load, let me write out what my del load, del I is. I think that's what's wrong, that when I do these, it may check out. You turn the volume down. Um, So we get all these things off the screen and kind of make an assessment of how we're different parts. Alright, so our Dell high is a little bit more than the Dell low. Dell high negative is actually more negative than the Dell low negative, so that's. Alright, so we got tweak our. Flip our side here. And have y'all figured out what this double ampersand thing means? So just while we're on the subject, that just means that both of the conditions have to be true for it to occur. So that means, there's a or that we can do too. Off the top of my head, I can't remember what the or looks like, but we can kind of Google it. It's just, Python's got the same thing, right, with or and equal. We'll cross our fingers, maybe this will work. Yeah, it could. Alright, here's the box. Alright, so we get some cool neighbors, and all we gotta do is just kind of cut and paste and do east and west the same way. Alright, so we're filling up north and south neighbors, and it's cool, we see some on the boundary, just on the top boundary, you don't have a neighbor still, so that's okay. Alright, so we'll take, Richard Petty out of here, and what we'll do is we go back and we'll put in, we're gonna do cut and paste, but we'll just do everything based on DX now. I'm actually gonna make this a little, this is one time, I'm actually gonna make this a little bit smaller. See what I'm doing. I'm sure y'all can still see that. Can still see that, I guess. So what I'm gonna do is, I'll just do that so I can get a good vision here. I'm gonna cut and paste this whole same column for argument right here. A whole bunch of paste things right here. So now we're gonna do same row. Okay, go back to the exec. I'll do this one. Forgot about that. I'll do same row. So we got an absolute value of dxa. So what we need to do is base this now on dya. Try to take out a few ones here. Alright. So we've got x we are to the east. And we'll do this two, that'll be the east. And if we are exits means we're to the west, so that's pretty cool. That wasn't actually bad. We got the two, that's wrong. Why do we got a two? Oh, yeah. Did I do that already? Yeah, that's we can do it here. That's gonna work on cross fingers. We can kind of do some sanity checks on just a random one right here. Alright, so let's look at, 330. So there's 330 in Nave. Yeah, kind of count back up here. I want to get one that's got all of them, so if I count up, go back. Let's see, one. I guess there's going to get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll call it 10. So we'll do Nave at 320, color 1. So it's found 4 neighbors at 320. And let's figure out what X is at 320. We'll check on all these. There's our X at 320, about 1896. So we'll do our X at 321. It should be right north, so it should have the same X value. Let's just check all the X values first, and we'll check all the Y values. So we got. So remember that 320 is the one we're checking. So we'll do the eastern one is 328. So that should be a little bit more. So a little bit more. And we'll do the southern one, which is 319. Should have the same X value. And we'll do the western one, which is 310. So it's not terrible, I guess. So we can say, so this should put us back to 1896. So it looks like all that part's working. So let's check the Y values, and then we can actually kind of move out of all this tedious stuff. So maybe we can actually do this. We can do this should be the northern neighbor, and it should have a little bit higher value. That's good. And we should do the southern neighbor, and it should have a little bit lower value, like almost 0. Should be 3. Good. We should do the eastern and western, they should be the same. Anybody have any questions on how this is kind of going? So it's the same. And the 4, which is the western, should be the same. That's good. All right, so hopefully if you've kind of been following along, cell phone picking and kind of going, that you should have something that's kind of close to this. Like I say, this is probably if you had me do this next week, I'd probably do something different. It's just one way of many that could be, this could be done. It's probably not the best. Sure, without researching, it's very unlikely that the first thing that pops in your head is the best. Just an idea. Okay. It's like the Larry the Cable Guy said, it's a get your run. All right. Anybody have any questions on that? All right. So that's actually pretty good progress. I'm happy with that. So the next thing we need to do is we need to go for and find all of our -777 flags, and then kind of take a look and see where we need to put boundary conditions. Okay. So let's think about how we can leverage that. So let me put some positive comments in here. So all right, so, did we talk about conditions we're gonna put on our, I think I drew them on the board, I'm not sure I took a cell phone picture of that. Did we talk about what boundary conditions we wanna put on the inside of the pipe?
Insulation on the.
For sure, that one's non-negotiable, or else we can't do axis symmetry. Although we could do anything we want to this, we could actually make a quarter pipe and put some loads on it, thermal loads, but we got an analytic solution for if we do actually have axis symmetry. I guess the first thing I want to do is on the inner radius, what do we say the temperature was going to be, or do we say the heat flux, or what do we say? I don't think I took a cell phone picture of that.
Did we have the initial temperature in there?
It was not any initial, but it's like a boundary
Boundary.
temperature. I mean, we're free to make up something if y'all don't care. Let's put some notes up here. Mine already has some notes. We got notes. So let's say, let's just take T to 100. And say that. And so my heat transfer folks know that we should get C1 log R plus C2 as our solution. And we're gonna do pretty well if we can do this. I guess then also just stands without saying, but you know why we do this whole exercise is we can come up with analytic solutions for a nice pipe because we know some math and fortunate we got like a way we can solve the equations of all the logs. But if we have like a brake rotor or something, it's got like some relief cut in for cooling, air cooling and stuff. Got like holes in it and so forth. If it's irregular shape, we're out of luck. So this method though, we'll kind of benchmark it. That's kind of what we do in numerical methods is we'll take a known solution, try out something new, we want to benchmark it against something we know. So we know the solution for heat transfer, so we're going to benchmark it against that. All right, so a couple of things here. We could set flags, and I'm going to propose that we set set two flags, so set BC flag 1. And as we're going through our Gauss-Seidel method, what we need to do is, as we're doing that crunch for things, we're gonna just keep setting, if there's a temperature flag, we're just gonna keep setting it to be what it is. And then if there's a BC flag, we're gonna have to make a little bit of adjustment there. Back in my mind, we're also gonna need the hard code of normal. So, and basically all we gotta do is say the normal vector, nx is, basically x over r. Actually, it should be, I wouldn't say plus or minus, plus. Actually, y over r. So we'll hard code that. Okay, we got something to do with our top product. All right, so let's do our inner BC flag and set that equal to 1 for that. So we'll search through all the things, and we're going to do two things. We're going to say BC flag and also set a BC value. So I'm going to say, all right, so we'll do this. What do we say the number of points is? And points sacrificial, not that. The keeper is the number of points. Alright, so actually, no, I'm not using K ever again. I'm done with that. We'll just initialize all the BC flags to also the minus 77. So I'll say, I'll do this. Set up, and we'll say, we'll initialize all these as like minus 77. So we'll say, we'll do, actually, we can leave the BC value as 0. It should be okay. You can actually throw another step in there if you like. All right, so all right, so what we need to do is we're going to get the BC flag, grab it for the inner part of the pipe. And this, again, this is just tediousness. So it's any way that you want to do this. Honestly, there is one way that you could actually do this, and you could have this read in as a file, and you could kind of do it by hand. So you could do it through CAD, and you could have, actually that's what most programs do, is they don't go through and they apply all this. They have what's called an input file, and they'll read the problem statement, which is nodes and like boundary conditions and so forth. But we don't have that. I thought about it, we could have generated that. You know, maybe if we get done, we may, at some point, we may wanna take this thing and copy it over to a generic, kind of a what we call a pre-processor, the finite element method, which involves meshing and setting loads and boundary conditions and so forth. We might do that so we can recycle it more readily for different kinds of problems. All right, so anyway, what we're gonna do is go through here and we'll say, actually, I could do this right here just as it is. And then I'm gonna say, all those are set to 777. I'll put some if statements in here. So those just kind of override it if it finds something different. So I'll say, rad. I'll just call this XW. So XW stands for X work. And that's going to be X of M, YW, YM. So I'm just going to check the radius here. I'll say that rad is equal to the square root of XW squared. Plus YW squared. And so what we can kind of do then is sort of check to see if we're approximately going to be on the boundary or not. That's a little bit of a tricky setup. That's a little tricky because we're kind of pixelated here, so we got to be very careful about if we're at the right radius and on the boundary. We actually could go back and leverage the left and right consideration. So I think if we're on the boundary, we're missing we'll be on the inner boundary, we'll be missing both a southern neighbor and or a western neighbor. Actually, yeah, that would work. All right, so I don't really need to do the right. Yeah, we can kind of do that. So and that way we'll check. No, we don't have to do this. So we'll say that. So we said western. So if we hadn't talked about it, that double equals, that means how you put equal signs in the conditional statements. Right? So actually, let's compute the radius and just do a check on there. So rad. And we'll just check rad, we'll just call this rad check and put it in there, see if it's working. All these should be about 1. I'm gonna do this. I'll leave that comment off and call it in. That should be cool. So let's run this. So we should get a bunch of actually 0.1s. This will be about what we get somewhere in that vicinity. This thing works, right? So our route checks are kind of around much. So we're going to do is set our BC flag there, and we'll say BC flag M is going to be, we said 1 with temperature, and we'll say BC value. It's very good. So let's do 100. What was that? So we got our temperature BC just put in. Okay. Am I got any questions on that? We still haven't gotten to the finite difference method. We still gotta get all these boundary conditions. We're gonna do the finite difference method. Alright, so, yeah, alright, so the other one's pretty easy. It's gonna be the two cut sides. So let's do those then. And one thing's kind of interesting, I'll have to think about this, is what happens right on the corner. So we got one corner node that will both be insulated on one side, and then it'll also have some applied temperature. I might like to do the applied temperature after the fact. So let's go here and put that one first. So I'll say, let's do the one on the right side. So XW is less than. I'm going to do set the BC flag equal to 2. Set the BC value of that flag be to the next order of business is we got the same thing for the Y values. So we got those two things set up. And last thing is we got to do the heat flux on the side then. So let's see how we can do that. So that would mean we're missing an eastern and a northern neighbor. So we'll say, do this thing right here. Paste this. We might call it good for the day to get all that working. So we're missing an eastern neighbor, that'd be 2. Missing a northern neighbor, that'd be 1. I do it for 2. And our BC flag is 2. With our heat flux, it's going to be 188. Actually, let's call that QN. Here's what change it pretty easily. And actually, since we're checking on that, all these should throw up a radius of about 2. So actually point to these cap that so short. We'll see a little exit there that's probably pretty cool. So we should see all these rad checks being around 0.2, and I'm pretty happy with that. It's close enough. Okay. All right. I guess the one other thing we could grab in here is we could get the normal. I don't like it starting. I'm going to call it the Z normal. So I just set these. That would got them to zeros. And if we're on the outside, that's the only time we really need the normal. Actually, we've got these two BC flags is equal to 2. Let's put the normals here. So, in that case, Z normal M 1 is equal to -1. So that's the normal there. Normal. So that's the outward normal vector. And for this case right here, let's say the normal. -1. And if we're on this edge right here, I mean, we don't need the normal right there. It's just not going to show up. Okay, here we do. And so let's see. We can only do this because we have a circle, right? So if we didn't have a circle, it's not completely just cast. And that's really good fire there. I like that. See if that runs, and we'll probably just plug it today. What I am going to do is check to see if the normals are working pretty well. The square of those should kind of all be the same. So if I say it is, it should be 1. So let's go up here and see if we find one that's. Yeah, we can take this one. It should be a vector. Crap is not pretty close. We'll call it here. It's kind of a unit vector. Probably as good as we're going to get. Okay, I'm going to propose the clause right there. I think we've got everything we need into the program. And then on Tuesday, we need to start doing the Gauss-Seidel method. So we got boundary conditions, normals, and connectivity of everything. So we're going to take a uniform guess. Since we got T is equal to 100, we're just going to take that as a guess. And then attempt to apply the Gauss-Seidel method to see if we can make that work. Anybody have any questions?